Perfect. I'm recording. So you said you had a problem with a question about the problem number 2 and 3, right?
Yeah, two. No, it's because you have like problem two different sections, right?
Uh-huh.
It's like problem two, and then
Which point?
it's basically yeah, two and three. Sorry, that was
2
from
and 3?
yeah, like
Okay.
from the problem two.
Oh, okay. 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 So this is problem 2, homework 5. Okay. So of course I don't solve like completely the problem, but I'm gonna just give you an idea how to solve, how to do the problem, right? So okay, so the problem number 2, this is so you have this vector field f, right? This is f, right? So let's see, so it's x squared cosine y sine z, and then sine y cosine z. All right, so first thing to do is you have to prove that f is a conservative vector field. I think so. I guess you know how to do that, and find the scalar potential function for the vector field f. So let's say you find the potential, the scalar potential function for f. So let's say so you do the first point, and then so we you know, so we know that f is the gradient of some function f, lowercase f. Okay, so f, where f is a function, where f, this is a function of 3 variables. All right, so once you do that, in number 2, so it says, well, you have to evaluate the vector line integral f, okay, along this path gamma. So the path gamma, it's gamma of t, it's t squared plus 1 e to the power t, and then e to the power 2t. T, the time t is in the interval 0, 1. Okay. So okay, so this is actually probably it's not it's actually easier than what you think, because of the following. You know, in the first so in the first point you prove that the f is conservative, and so it's the gradient of some potential function f, right? So what we proved in class, guys, is that so if you know that f is conservative, and f is the gradient of some potential function f, then actually the vector line integral, this vector line integral, okay, only depends on the value of the function f at the initial and terminal points, at initial and terminal points. So in other words, so we're going to use the fact, that this f, vector field f, is the gradient of some function f, and so we can say that this vector line integral along gamma, okay, which is because this vector field f is the gradient of some function f. So this vector line integral along gamma, it's just equal to, so you don't have to parameterize gamma, okay? So you can just forget about the gamma, and this vector line integral would be just equal to the function f evaluated at the terminal point. So the terminal point, so this gamma of t, so this is a path, right? Gamma of t is a path. So it goes from, this is gamma of 0, that's the initial point, to some terminal point, gamma of 1, okay? So you're moving from gamma of 0 to gamma of 1. And what I'm saying is that this vector line integral, because your function, your vector field is the gradient of some function f, then this is just a f of the f of terminal point, so f of gamma 1 minus f of gamma 0. Okay. The function f, of course, this function f is the function you get in the first the first point. You have to prove that f is a vector field is conservative, and you have to find this function f, right? This lowercase f. So when you find the lowercase f in the first point, then you can use it, okay? You can use it to find this vector line integral. So gamma of 1, for example, here, gamma of 1 would be, just replace t by 1. So that would be like 2 e to the power 1, e to the power e squared, okay? Oops. So this is e squared, okay? So, here, this is just f of 2 e squared minus f of gamma of 0, so t is 0. So that will be 1, e to the 0 is 1, and e to the 0 is 1. So that's f of 1, 1, 1. Okay. So all you have to do is just to evaluate this function f. Again, you got this function f in the first point, right? So you evaluate the function f at this terminal and minus the value of the function f at the initial point. Does this make sense to you?
Yeah. Thank you.
Okay, so you don't worry about the gamma. You don't have to parameterize the gamma. Okay, you can just forget about the gamma.
Okay.
That's actually the thing. When you have this conservative vector field, you can just forget about the path, and you only worry about the initial and terminal point. That's what really matters here: the terminal and the initial point. But of course, you have to find first this function f. Okay.
Yes.
Okay. Okay, so if this answers your question about, so you said the problem P, right?
Yeah. But
Okay,
I
so
understand this one now.
the problem P is this, the idea is the same. So you have this vector field F, and so the work done by F is, let me just write down here at least the formula for you. So just to remind you, this is problem P. Right. So the work done by this force field F, it's just by definition, it's this vector line integral. Okay, along, so you are in moving a particle from the point, so from the point A to the point B. Okay, so you're moving from this point A to the point B. Okay, there's this point A, there's this point B. Okay, the thing is, so we have to prove that this vector field F is conservative. So if F is conservative, it means that F is a path and dependent line integral. Okay, so it doesn't really matter which path you're gonna take from A to B. Okay, you can take any path. Let's say this is gamma, or you can take a different path. Let's say this is beta or alpha. Okay, it doesn't really matter the path you take from A to B, because this integral is going to be just the difference of the value of the function f at the initial point, so the terminal point, which is B, minus f of A. Okay, so as I said, here it doesn't matter which path you're going to take, gamma or beta or alpha. Okay, because the answer is just this difference of the value of f at terminal and initial point. Okay, but you have to find, of course, this function f. So you have to prove that this f is conservative, and then you have to find the scalar function f. Does this answer your question about problem 3? It's basically the same as the problem number 2. You have to do all the steps that you did in the problem number 2.
Okay. Yeah.
Okay.
Yeah, kind of good.
Okay, so what you have to do is, first you have to prove that f is conservative.
Yeah, that was the first part, and
yeah. It's just in this problem number 3, it doesn't I mean, it doesn't say what you have to, what the steps you need to do. But it's the same steps as the problem two. It's like you have to prove that f is conservative. You have to find this function f says that vector field f is the gradient of this lowercase f. Okay, and once you find this f, then you can just use it to find the work done by the force field f or vector field f.
Okay.
This is just the same steps as the problem two. It's just yeah.
Okay, I got it.
Perfect. Any other questions, guys? I hope you understand how to. Well, like in the problem number one, you have to determine whether f is conservative. So to determine whether f is conservative, guys, all you have to do is just compute the curl of f. Well, I mean, it depends. If f is two-dimensional vector field, like if you have just two variables, all you have to do is to compare, the derivative of, let's say, the second function with respect to x to the derivative of the first function with respect to y. Okay, and if it's a three-dimensional vector field, if you have like three different variables, then you have to compute the curl of f. Okay. All right. Any other question, guys? I don't know, David, Anicia, if you have any questions about the homework. All right. Okay. Sounds good.
Those are the only steps. First, we prove that it is conservative, and then
Yes.
the scalar product.
Yes. So, you're talking about the problem number 3.
Yeah, number 3 and 2.
Yeah. So you prove that it's conservative, and then you have to find this function f, such that f is the gradient of this lowercase f. So this find f. This is like in the problem number 1. So you have, remember how we found this find this function f is we had to integrate like you integrate the first the first component with respect to x, and then you derive with respect to y, you compare it with the derivative with respect to y, etc., etc. I mean, you can find example. I mean, we did plenty of examples, I think, like a week ago. Yeah, but yeah. So yeah, you have to do these first two steps here, and then this would be the answer.
Okay.
Any other questions, guys? All right, nice. Okay, so this is yeah. So we're gonna continue with the surfaces, right? I mean, we did a lot of different integrals for along the paths and curves, right? And so we're gonna do the same for surfaces. So we're gonna compute like the vector surface integral. We're gonna compute the scalar surface integral. So we're gonna do the same for surfaces. But first, we're gonna compute the area of surfaces. I'm gonna see how to use the parameterization to compute the area of any surface. All right, so okay, so let's continue with this section. So this is section 7.3. Parameterized surfaces. So I'm gonna just remind you what we did the last week very quickly, and then I'm gonna define the tangent space to a surface, and then we're gonna compute the area of a surface. So first, let me just recall. So what's the parameterization of a surface? So a surface S. So again, guys, a surface that's a two-dimensional, it's a two-dimensional object, right? It's two-dimensional. So if it's two-dimensional, it means that you need the two parameters, right? So a surface, which is a two-dimensional object, is the surface S. That's called the surface S. So it's parameterized by a function, let's say function phi, from so some region in R2 to R3. Okay, and as I said, it's two-dimensional, so you're gonna need two parameters, not only one. So if you have one parameter, you have a path, you have a curve. If you have two parameters, then you have a surface. So we're gonna have x of uv, so that's a function of uv. Y, the second component is gonna be some function of uv, and the third component, which is the z coordinate, is gonna be also a function of uv. So example, I mean, we had a lot of examples last week, but let me just give you another example. So I don't know. I mean, probably in Calc 3, guys, so you discussed the graph of a function of two variables, and you said the graph of a function of two variables that will be a surface. So a surface S. So the graph. So the graph of a function of two variables, a function f. So f is a function from R2 to R. So f is a function of two variables. So the graph of such a function f is actually, it's a surface. Okay, as a surface. So for example, let me just give you a numerical example. So let's say f of xy, so it's a function of two variables, right? So is equal to x plus y. Okay, so this is a function of two variables, but like this is like what we do for a function of single variable. So if you have a single variable like f of x, right, and you want to graph f of x, then you're gonna need another axis, the y-axis, and the y-axis. So the y would be equal to f of x, right? So what I'm saying is, so if you have a function of a single variable, then if you want to graph f of x, you're going to need another coordinate, let's say or another axis, the y-axis, and so the y would be equal to f of x. Okay, so in this case we have two variables, x and y. So to graph, if you want to graph this, you're going to need a third axis, right, or a third coordinate. So to graph f, we need a third axis, the z. So z would be equal to f of xy, right? So like here in this example, so f of xy is equal to x plus y, right? So I want to graph this. Well, at least sketch the graph of this function, okay? So then my z would be equal to f of xy. So z is equal to x plus y, okay? And so what we do, guys, so why do we obtain a surface? Because, so you have two axes here, x and y, and there's this third axis, the z, right? And so when you say, for example, here, like you say f of 1, 1, what will be f of 1, 1? F of 1, 1 is 2, right? So what we do, guys, is we take a point. So let's say this is here, this is 1, 1. So we take this point 1, 1, right? And we are saying f of 1, 1 is 2. So f of 1, 1 is 2, right? This is 2. So this would be the point 1, 1, 2, right? The z would be 2. So what we do is, so for each x and y, so we can take, of course, another value of x and y. For example, f of 1, 2, that would be 1 plus 2, and that would be 3, right? So what we do is we take this point here on the plane, the xy plane. This is the point 1, 2, and you associate the image, which is 3. So the image would be somewhere here, let's say. So that's 1, 2, 3, right? And so what we do, guys, so we can imagine, so what we are doing is we are taking points on the XY plane, like this point here, or this one here. Okay, so to each point on the XY plane, we associate an image. So like this point here goes somewhere here, this point here goes somewhere here, etc. Right? And it's like you're taking all the points on the XY plane, and to each point you associate an image. And so what we are doing, geometrically, is that you are taking this XY plane, the horizontal plane, the XY plane, and so the graph of this function f would be just you can think of the graph of f as a twisting of the XY plane. So you're just twisting the XY plane, and you're gonna have this. You're gonna have this surface. So this surface. This is the graph of f of xy. And it's a two-dimensional, right? It's two-dimensional because again, basically the idea is you're taking points on the XY plane, and to each point you associate an image, right? So basically you're taking the XY plane and you're twisting the XY plane. Okay, so you get a surface. As I said, a surface, you can think of a surface as a twisted plane, right? It doesn't have to be a flat plane. It can be just some twisted. You take a sheet of paper and you twist your sheet of paper, right? And that will be your surface, or the graph of the function f of xy. Does this make sense to you guys? You see why the graph of f of a function of two variables would be a surface, right? So that's the idea. So this is my surface S. Okay. Now, so this is a surface. So I want to parameterize such a surface. Okay. So let's parameterize the surface S given by the graph of f of xy. Okay, which is in this case is just x plus y. Okay, so what we can do, guys, the simplest, I would say, parameterization of such a surface, so a surface given by the graph of function f, is just, you can say, well, my x coordinate is equal to u. Remember, you want to parameterize, so you're going to need two parameters, right? So all you can do, so the restriction here is that f of xy, that will be your z coordinate. So z is equal to f of xy. So if you say x is u, y is v, because there is no relation between x and y. So x could be any number, y could be any number. So x is u, y is v, but z, it must be equal to the, it's a graph of this function f. So the z coordinate must be equal to f of xy. Okay, but x is u and y is v. So this is f of uv, which is, u plus v. Okay, so if you want to parameterize a surface given by the graph of some function f, all you have to do, guys, is just to, then the parameterization is given by the function phi, where phi is the parameterization of the graph of f of xy is, so phi of uv. So x, we said x, there's no restriction on x. X could be any number. So let's say x is u. Same for y. So y is v. But then the restriction is on z. Your z must be equal to the function f of xy. So z is f of uv. So in this case, that will be u, v, and then u plus v. Okay, because my function f of xy, it's equal to x plus y, so that's u plus v. All right. So you see how to parameterize a graph of parameterize a surface given by the graph of some function f, right? So it's quite simple. All right, so that's for parameterization. That's an example. Now tangent vectors. So we discussed the tangent vectors to the surface, and there are two, let's say, two distinguished tangent vectors to the surface. So tangent vectors. So you have a point P of the surface. So point P. It's a point of the surface. So that's the point P. So that's the image of u0, v0 under the function phi, the parameterization. So at that point, so again, guys, you can just imagine, you have your surface S is somewhere here. This is your surface S, right? This is my surface S. And so we have some point P here somewhere. So this is my point P, right? So point P is it's phi of some u0, v0. U0 and v0 are just fixed numbers. So we have this point P, and we said that at the point P we have two tangent vectors, two special tangent vectors. So the first tangent vector is just the derivative of phi with respect to u. So let's call this is we call the first tangent vector, I think, a capital T index u. So at the point P. So this is just derivative of x with respect to u, derivative of y with respect to u, and then derivative of z with respect to u. Okay, so this is the first tangent vector. So it's a tangent vector to the surface. Okay, tangent vectors to the surface. Okay, they are tangent vectors to the surface because they are tangent vectors to curves lying on the surface. Okay, so so here's my, let's say this is my capital T index u. Okay, and we have a second special tangent vector to the surface. It's T index v. So at the point P. So that will be derivative with respect to v. Okay, so we have a second tangent vector. This is T index v. Okay. Okay, so we have these two tangent vectors, and then there's this notion of smooth and regular. So we have to suppose, as I said, we had the last time we had this example with a sphere. So we suppose that we need this parameterization to be one-to-one. So we suppose that the parameterization phi. So this is really important. That phi, the parameterization is one-to-one. Okay, in some region R, let's say in a region R. Again, so what does it mean one-to-one? It means that if 2 points, they have the same image, then the 2 points are equal. Okay, so in other words, so one-to-one. I'm going to give you an example in a couple of minutes, guys. So one-to-one means if phi of u1 V1 is equal to phi of U2 V2, right? So 2 points, they have the same image by the function phi, then they are equal. Then U1 V1 is equal to U2 V2. Okay. So we need this assumption, this hypothesis, it's a 1-1-1-to-1 to check that that the surface is smooth. Then the surface S, which is the image by the function phi of this region R. So this surface S is smooth or regular at the point, let's say at the point P. Okay, if so, this point P in this, of course, in this our surface, if the cross product of the two tangent vectors of these two tangent vectors is not zero. It's not the zero vector. Again, guys, this is a cross product. The cross product of two vectors, it's a vector. Okay, it's different from the scalar product. Scalar product, the answer would be a number, but cross product, the answer would be a vector. So this is different from the zero vector. So if this is different from the zero vector, then your surface S is smooth or regular at the point P. Okay, so we had a couple of examples last week, but let me give you one more example. So let's take this example where the surface S is the graph of some function f. Okay, so S is the graph of some function f. Okay, as I explained in the in the beginning of the lecture, so you can see the graph of function f of two variables as a surface, right? So let me just remark here that so the parameterization of S in this case, so we said phi in this case, phi of uv would be u v, and then the z, it must be equal to the function f because that's supposed to be the graph. So the z must be equal to f of xy, but x is u, y is v, so it must be equal to f of uv, right? That's my parameterization, the parameterization of the graph of f of xy. Now, let me just remark here, this parameterization is 1-to-1. It is 1-to-1. Okay, because, well, if, phi of u1, v1, so f of u1, v1, that's u1, v1, f of u1, v1, all right? So if this is equal to f of u2, v2, which is, by definition, it's u2, v2, f of u2, v2, right? So these 2 points, they have the same image by the function phi. So if they are equal, the images are equal, so then this first component is equal to this first component. So u1 is equal to u2, and then you see v1 is equal to v2. Okay, so then u1 is equal to u2, and v1 is equal to v2. Okay, because they must be equal. So what I'm saying is, if you have the same image, then we have at the same point. Okay, so that's what I call one-to-one, right? You have same image, then the points must be equal. Okay. Anyway, so all I'm saying, guys, is that this parameterization is one-to-one. So we can check. So let's check. So let's see where. So the question now is to determine where the S is smooth. So the question. So determine where the graph, the surface given by the graph of function f is smooth. So determine where S is smooth. Okay, so again, parameterization is the following. Phi of uv, it's u, v, and f of uv, all right? Now, so you want to see where this is smooth. So you need to compute the tangent vector t index u. So that's just a derivative of x with respect to u, derivative of y with respect to u, and derivative of z with respect to u. Okay, so again, guys, this is my x, this is my y, and this is my z. Okay, as a function of uv, of course. So partial x, partial u, x is u, so derivative is 1. Y is v, so derivative of y with respect to u is 0 because v is a constant. And then we don't know the explicit expression of f, it doesn't matter. But derivative, so derivative of z with respect to u, that will be partial derivative of f with respect to u. Okay, so that's my tangent vector t index u. Again, guys, if you have any questions, just let me know, right? You can stop me at any time. Now the second vector, it's the tangent vector index v, so t index v, so partial x, partial v, partial y, partial v, and then partial z, partial v. So derivative with respect to v, u derivative of u with respect to v, that's 0. Derivative of v with respect to v is 1, and then derivative of this function f with respect to v, well, it's just partial f partial v, because we don't know. I mean, my function f is here is just some random function. Okay, so we don't have the explicit expression of f, but it doesn't matter because when you take now the cross product of these two tangent vectors, so we want to check where it's smooth. So you need the cross product of these two vectors to be non-zero. Okay, so let's see where the cross product is going to be 0. So if you do now t u cross tv cross product. Okay, so again, guys, if you have trouble with the cross product, just let me know. But if you want to do the cross product, then basically what we do is you take first you cross multiply here. All right, so if you cross multiply there, that will be minus derivative of f with respect to u. Of course, we have 0 times derivative of f with respect to v, so that will be 0 minus 1 times derivative of f with respect to u. Now for the second component, we take we cross multiply here. Okay, so this is so that will be so it's minus derivative of f with respect to v. Okay, and then last component, so we have to cross multiply here. So that's 1 times 1 minus 0 times 0, so that's 1. Here's my 1. That's my third component. Okay. Now, well, of course, so we have to compare this to the 0 vector, right? I mean, this derivative here, of course, could be 0 at some point. This also could be 0 at some point, but 1, last component is always equal to 1, so it's never 0, right? So this vector is different from the 0 vector for any uv, right? It doesn't matter the values of u and v, because the last component would be always 1, which is non-zero. Okay, so this is always non-zero, always non-zero. So it doesn't matter the value of u and the values of u and v, last component is always non-zero. So the graph, so what we are saying here, guys, so the conclusion is that the graph of, so the surface given by the graph of f of xy, so the surface S given by the graph of f of xy is smooth everywhere. Okay, because it's this cross product, it's never 0 everywhere. Right. And as I said, so I mean, in theory, whenever you want to check if a surface is smooth, when you are using some parameterization, you have to make sure that the parameterization is 1-to-1. Okay. But again, I want to make sure, I'm going to make sure, like in the tests or in the homeworks, that the parameterization are 1-to-1. So we don't really have to check it there 1-to-1. Okay. And that's actually, it's missing in the textbook. There's a mistake in the textbook. So we need this condition to be the parameterization to be 1-to-1 in order to check the smoothness of or regularity of the surface. Anyway, any question, guys? Okay, no questions. Then, so that's for the smoothness. Now today, as I said, we're gonna discuss first. Today, I'm gonna first discuss the tangent plane. Okay, tangent plane to parameterized surfaces. Tangent plane to the surface S. Okay, so what's the definition of the tangent plane? It's actually quite simple. So if you have a parameterized surface, which is a smooth, so you need the surface to be smooth at that point. So if parameterized surface S is smooth, so you need the smoothness, assumption. So it's smooth at some point P, which is phi of, let's say, u0 v0. Then we define, so the tangent plane at P is going to be the plane spanned by the two tangent vectors t index u and t index v. Okay. Then we define the tangent space to the surface at the point P, tangent plane to S, to the surface S at the point P. So to be the plane passing through P, of course, to be the plane passing, of course, through P, and having so TU cross TV as a normal vector. So what I'm saying is that, so here, let me just draw some picture. So this is X, Y, and Z, we are in the space. So we have some parameterized surface. Here's some surface S. This is my surface S. Okay, this is my surface S. Surface S. On the surface S, we have a point, some point here, P. There's this point P. Okay. And at P, we have two special, like, distinguished tangent vectors. There's this T U at the point P, and there's a second tangent vector, this vector here, TV at the point P, right? So we have two tangent vectors, and what I'm saying here, guys, is that the tangent plane to the surface S at the point P would be the plane spanned by these two tangent vectors and containing the point P. So that will be this plane here, somewhere here. Okay. So this plane contains the point P. It contains the point P, of course, and it's spanned by these two tangent vectors. And of course, if you take the cross product of TU with a TV, that will be a vector which is actually perpendicular to the plane. So here, so this vector here, this would be TU cross TV. Okay, so remember, guys, when you take a cross product, you get a vector which is perpendicular or orthogonal to the initial two vectors. Right. So this TU cross TV, this is perpendicular to TU, and it's also perpendicular or orthogonal to TV. All right, so let's have some numerical example, and then I will give an exercise where you have to find the equation of the tangent plane. So, example. Okay. Let's say I'm gonna take an example of a single cone. Okay, again, single cone is just this cone here in the top. This one here. Okay, this is my single cone. That's a surface, of course. Right, it's a surface. So, of course, parameterization of a single cone is f of uv is u cosine of v, u sine of v, and then u. U must be positive. The height, the z, is equal to u, and it's positive or 0. And then v is just our angle, and so it goes from 0 to 2 pi. Anyway, so the question is, you need to find the tangent plane, the equation of the tangent plane. So when I say find the tangent plane, of course, it means that we need to find the equation of the tangent plane. So find the equation of the tangent plane to the single cone. So the surface is that's my single cone. So to the single cone at the point P. Single cone at the point P. Let's say P is phi of 1 and pi over 2. Okay. So U is 1 here, and V is pi over 2. So if U is 1 and V is pi over 2, then what will be P? So then P is, so this is equal to, so cosine of pi over 2 is 0. So that'll be 0. Sine of pi over 2 is 1 times 1, that will be 1. and U is 1. So that will be the point 0, 1, 0, 1, 1. Okay. So P, the point P is 0, 1, 1. Okay. So it's gonna be, let's say, it's somewhere, let's say here. Okay. It's 0, 1, 1. 0, 1. That's my point. And the question is, I need to find the tangent plane to the single cone at the point P. Okay, again, here you can imagine you have your tangent plane to the single cone at the point P. So we have to find the equation of the tangent plane. All right, guys. So let me just remind you the formula. So how do you find the equation of the tangent plane? So the tangent plane, I mean, it passes through P, okay, and has a normal vector TU cross TV. Okay, so let me just remind you in general. So the equation of a plane. So if a plane passes through, let's say P, which is x0, y0, z0, and has a normal vector. I think you, I guess in Calc you computed the equation of planes. So in this case, so it has normal vector, let's say n, given by, let's say, a, b, c. Then the equation of the plane is a times x minus x0 plus b y minus y0 and plus c z minus z0 equal to 0. Okay. So again, x0, y0, z0, that's the coordinates of my point P. And of course, a, b, c, that's just the components of my normal vector, right? That's the equation of the plane. Let me just remind you, I mean, what's the geometric idea? Why do we have such an equation? Well, the idea is very simple. It's because so the idea is that you know, you have your plane. This is my point P, right? And here's my normal vector n, right? This is normal to the orthogonal to the plane, right? Now, if you take a random point which belongs to the plane, let's say this is a point, this is point x, y, z, right? So the idea is the vector going from P to x, y, z. So this vector from P to x, y, z, this vector, because x, y, z is supposed to belong to the plane, right? And P, of course, belongs to the plane. So then the vector going from P to x, y, z lies on the plane. It belongs to the plane, right? So then this vector should be orthogonal to the normal vector n. Okay, so then the idea is that you know, x, y, z of course, let's say this is the point P with coordinates x0, y0, z0. So the idea is that x minus x0, the vector x minus x0, y minus y0, z minus z0. So that's the vector going from P to x, y, z. This is you know, orthogonal to n. And so if you use the scalar product, then the scalar product of these two vectors would be 0. Scalar product with ABC, this would be 0. Okay, so that's why we got 0 here, and this is just this scalar product. Scalar Anyway, so just to remind you why we have such an equation, right? Now let's come back to our exercise. So we have the point P, the point P, so it's 0, 1, 1. So that will be, this is my x0, this is y0, z0, right? Now I need to find the normal vector, the ABC, right? So the normal vector is just the cross product of TU with TV, right? So let's just come back to our example. So our n is TU at the point P cross product with TV at the point P. Okay. So again, the point P is the point 0, 1, 1. So it's a phi of 1 pi over 2. So it's 0, 1, 1. Okay. Now, phi of uv, that's parameterization of the single cone. It's u cosine v, u sine v, and u, right? So let's compute the cross product. So then this is, so derivative with respect to u, that will be cosine of v. Derivative with respect to derivative of the second component with respect to u, that would be sine of v. And then derivative of u with respect to u, that would be 1. Okay. Now this is, so cosine of v, sine of v, 1. That's my tangent vector index u. Now at the point P, what's the value of this vector at the point P? At the point P. So at the point P, it means that this is my point P. So the u is equal to 1 and the v is pi over 2, right? So u is 1 and v is pi over 2. Okay. So then that will be the vector. So cosine of v is pi over 2. So cosine of pi over 2 is just 0. Sine of pi over 2 is 1, and there's 1. So that's 0, 1, 1. Right? Do the same with the derivative with respect to v. So derivative with respect to v, u cosine of v, derivative of cosine of v with respect to v. So that'll be minus u sine of v. Derivative of sine of v, that's cosine of v. So it's u cosine of v. So again, this is a derivative with respect to v, right? And then derivative of u with respect to v is of course just 0. Now at the point P, so at the point P, again, u is 1 and the v is pi over 2. So that will be sine of pi over 2 is 1. So that will be minus negative 1. Cosine of pi over 2 is 0 and then 0. Okay. So now I can find my normal vector. It's just a cross product of these two vectors, right? So my n is, so it's tu at the point P cross product with tv at the point P. So that'll be equal to, again, guys, have trouble with cross product, just let me know. So here is going to be 0, and then going to be positive 1, and then it's going to be minus, that'll be a positive 1. Okay, so this is my normal vector. So this is like my A, B, and C, right? And again, the point P is phi of 1 pi over 2. And that's 0, 1, 1. So again, this is my x0, this is y0, z0. So the answer, the equation of the tangent plane, so the equation of the tangent plane to the surface of the single cone at the point P is Well, again, remind you the equation of the plane. So it's supposed to be a x minus x0, right? Plus y, plus b y minus y0, and then plus c z minus z0 equal to 0. So in our case, a is 0, x minus x0 is 0, plus b is 1, y minus y0 is 1, plus c is 1, z0 is 1 too. Okay, is equal to 0. So that will be y minus 1 plus z minus, is that correct? Yes, plus z minus 1. So that will be y equal to 0. So that's y plus z minus 2 is equal to 0. So in other words, that's y plus z equals to positive 2. Okay. Any question, guys? Again, this is the equation of the tangent plane to the surface, to the single cone at the point P. All right. So here's an exercise. So if there's no question, so here's an exercise. So it's a similar problem. So let's say you have the surface S given by the parameterization. So phi of uv, let's say it's u cosine of v, u sine of v, u squared plus v squared. Okay, so the question is find tangent plane, the equation of the tangent plane to S, to the surface S at the point, so P at the point P equals 2, so it's phi of 1, 0. That will be the point. So U is 1, V is 0. So there'll be 1, 0, and then 1. Okay, guys, let's say you have 5 minutes to think about this problem. So you have the point, all you have to do is to find the normal vector to the tangent plane. So as I said, guys, so after this, we're gonna do the area of smooth surface. Probably, I think we're gonna have a chance to finish the area of the surface today. Well, I'm not sure, but anyway, so after the area of surface, we're gonna compute integrals on surfaces. So we're gonna compute the scalar surface integral and vector surface integral, as we did for line integrals. And then we're gonna move to the main theorems in this course, Stokes and Stokes and Gauss diversion theorem. And then if we have, time, we still have time, we're gonna do probably one more section about differential forms. So what we are doing, guys, is it's a sort of introduction to differential geometry. I mean, tangent vectors, tangent planes, parameterization of paths or surfaces, etc. Um, so that's part of introduction to geometry. I mean, if you if you take a course in an advanced course in geometry, let's say, then you would start with this parameterizations, etc., etc., tangent planes, tangent vectors. Okay, so these notions are just like uh, uh, the foundations of geometry. Because all these notions, they allow us to study or classify. Let's say you want to classify objects like surfaces. So you would need all these notions, to distinguish between different surfaces. Anyway. I mean, concrete example of a surface, of course, would be Earth, right? The Earth is a surface. I mean, we are living on the surface, right? That's the Earth, right? That's a two-dimensional space. Okay. And I mean, you for example, layer. So we're gonna complete the area of a smooth surface. So as I said, Earth, it's an example of a surface. And if you want to complete, let's say, the area of the Earth, then all you have to do is to apply our formulas. Um, so I'm going to show you later in a couple of minutes how to compute the area of any smooth surface. Anyway, okay, guys, I don't know if you had time to try this exercise. So, okay, so let me just probably go over this exercise. And again, if you have any question, just let me know. So this is, so you have this surface, that's the phi here, it's a parameterization of our surface. We have the point, and we need to find the equation of the tangent plane. Of course, tangent plane here, I forgot the plane, tangent plane. All right, so what we really need, so step one, I would say, is to find the tangent vectors. So first, tu, that's the derivative with respect to u. So that'll be cosine v, sine v, and then 2u. Okay. Now at the point P, so that point P, u is 1 and v is 0. So u is 1, v is 0. So that will be cosine of 0, it's 1, sine of 0 is 0, and 2 times 1, it's 2, right? Now, tangent vector t index v, derivative with respect to v, so derivative of cosine, it's minus sine, so it's minus just u sine of v. Derivative of sine is cosine, so that's u cosine of v. And then, of course, 2v, okay? And now at the point P, so again, point P, u is 1 and v is 0. So u is 1. So sine of 0 is 0. Cosine of 0 is 1 times u, which is 1. And 2v, v is 0. So it's just 0. Now the normal vector n. So it's, of course, it's t u at p cross tv at p. So that would be, again, if you have trouble of the cross product, let me know. So first we're gonna have minus 2, and then we're gonna have 0, minus 0, so it's 0, and then we're gonna have 1. Okay, that's my cross product. And so the answer, so the equation of the tangent plane to the surface S at the point P. So so this is supposed to be my A, this is my B, this is my C. Now the x0, y0, z0. So here's x0, y0, and z0, right? So it's A. So A, x minus x0 again, plus B, y minus y0, plus C, z minus z0, 0. So A is 2, so it's -2. X minus x0, x0 is 1, plus B is just 0, y minus 0, plus C, which is 1, z minus z0, it's 1. 0, so that's minus 2x plus 2 plus z minus 1. So the answer would be minus 2x plus z. 2 minus 1 is positive 1. The other side would be negative 1. So here's the answer. All right. Any question, guys? Okay. No question then. So that's for the tangent planes. And so we are done with this section 7.3. We did the parameterization, we did the tangent vectors, we did the tangent plane. Now we can move to the area of a smooth surface. So this is section 7.4. So we're going to compute area of a smooth surface. So this is very powerful. We're going to have very powerful, formula to compute the area of any surface. I mean, it doesn't have to be. Remember that we use the double integrals to compute the area of surfaces, but our surface. Remember, we had the condition that the surface must be an elementary region in the plane. All right. So here, our surface S, our surface doesn't have to be elementary region. Okay. So so this is more powerful than what we had. So this is more powerful than what we had in section in chapter 5 with the double integrals. Then what we had in chapter 5. So again, chapter 5. I remember in chapter 5 we used double integrals, to compute area of the surface. But the surface, we said in the chapter 5, the surface must be elementary region. So of an elementary region in the plane, right? Of an elementary region in the plane. Okay, but here in this case, in this section 7.4, so we're going to compute the area of a surface. It doesn't have to be elementary region in the plane. Okay, all we need is that. So we have to suppose. So we have this parameterization. Okay, so the idea is the following. So suppose a surface. So we have a surface S given by, so some parameterization phi. So again, phi, it's a map from some region in R2 to RP. Now, so phi of UV is X of UV, Y of UV, and Z of UV. Okay. We need to compute the area of the surface here. We need one hypothesis. So we need that this parameterization. So we need this parameterization phi to be 1-to-1. So phi must be 1-to-1 and smooth, except possibly at the boundary of the region D, at the boundary of D. Okay. So we see in examples how does it work. Okay. So again, because my map, my function phi, it goes from this region D in the plane, right? So we need phi to be 1-to-1, okay, and smooth, except at the boundary of this, possibly at the boundary of this region D. All right, guys. So how can we compute the area of the surface? So I mean, the idea is the following. So the geometrically, so let me give you an idea to see how we can we get the formula for the area of this surface S. So we start with, you know, we have two parameters, U and V, right? We have two parameters. This is U, this is V. Okay, and so we have some region D here. This is my region D. Okay, and then so we have this map phi or function phi. So this is phi here. So phi goes from D to R3. So here we're gonna have R3. So R3, of course, we're gonna have X, Y, Z. This is X, Y, and Z. And so the image of D by the function phi would be some surface. So here's my surface. This is my surface S. Okay, so this surface S, again, that's the image of D by the function phi. All right. So the idea is, as usual, guys, I mean, like what we did, like, you know, when you compute the area of elementary region, or you want to compute the volume of some solid in the space. So what you do is, you know, you divide your surface or your solid. Let's say in this case you have a surface. So you divide your surface into very small, you know, very small rectangles. Okay, so then you approximate the area of these very small rectangles, and then the total area would be the sum of all these very small rectangles, right? And then you have to take the limit going to infinity. It means that the rectangles that are getting smaller and smaller, so we have a better approximation of the area. And at infinity, when you take the limit, they'll be equal exactly to the surface, to the area of your surface, right? So what I'm saying is that we start with a very small rectangle. So we take a small rectangle here in D, right? Let's take a small rectangle here. Okay, so you can imagine, guys, so we have here, there's these two vectors. Okay, so here, this side here, let's call this side here delta u. Okay, the length of this side here is delta u, and the length of this side here, the other side here, is delta v. Okay, so you have this rectangle, very small rectangle, with one side equal to delta u and the other side it's delta v. Okay, now what's the image of this rectangle by the function phi? Well, the idea is, of course, let's say you take here, this is the point, let's say this is the point u0 v0. Okay, so you're taking this rectangle with so a vertex of this rectangle is the point u0 v0. So here somewhere this is p, which is the image of u0 v0 by the function phi. Okay, now you compute the image of this small rectangle with the vertex at u0 v0 and with the sides, length of the sides delta u and delta v. So then actually the image would be, so you see, so this is so the sides of this rectangles here, this rectangle here, so you have this delta u delta v, right? So the image would be, so you're gonna have a parallelogram. So it's not necessarily a rectangle, you're gonna have like a parallelogram. Okay, and you're gonna have two vectors. Okay, so this is a parallelogram. Okay, which is the image of, that's the image of this rectangle, the small rectangle in the region D, right? The image of this rectangle. So this is delta u and this is delta v. Okay. All right, guys. And so again, do you think of this rectangle? They are very, very small, very, very small rectangles, right? And so when they are very, very small, so then you can just approximate this very small rectangle using vectors in the tangent space. So, and so I claim that the image here would be a parallelogram spanned by the vectors. So this is going to be a parallelogram. So spanned by the vectors. So the image, so this is supposed to be a vector here. You know, you have a vector here, of length, of course, magnitude delta u and magnitude delta v. Okay. So the image would be, so parallelogram spanned by the vectors delta u, that's the magnitude, times the vector t index u at the point P, of course, here, and delta V times, so delta U, delta V, they're just numbers, right? They're just the length of my, the length of the sides of my rectangle. T index U, T index V, they are vectors. All right, so this is at the point U0, phi of U0, V0. Okay. Now you want to approximate. Okay, so we want to approximate the area of this small parallelogram here. Okay, so the area of this parallelogram, it's given by, remember, if you have a parallelogram spanned by two vectors, let's say vectors u and vector v, then the area of the parallelogram is just the magnitude of u cross v, right? So just to remind you guys, so if you have a parallelogram, So the area of parallelogram spanned by two vectors u and v is just the magnitude or the length of the vector u cross v, right? So the parallelogram here is just a, so you know how this is u and this is v. Okay. So all I'm saying, guys, is that the image of the rectangle here can be the area of the image can be approximated by the area of this parallelogram. Okay, so then so we can approximate the area of, so the image of this small rectangle, the area of this small rectangle here by magnitude of, you know, so we have this first vector here, and this is my second vector. So it's delta u, tu at the point P, cross product with delta v, tv at the point P. Okay. So again, delta u and delta v, they're supposed just to be numbers. That's the length of the sides of our small rectangle. So they're just numbers. I can them out. So this is just equal to, you know, cross product, the magnitude of the cross product of tu with tv right, and you can put the delta u, delta v here. Okay, because again, delta u, delta v are they're just numbers. So you can just pull them out of the magnitude of the cross product. Now, so as I said, you wanna compute the surface, the area of this the surface S, right? So all you have to do, of course, is you know, to add, you know, we have all these small areas here. That's again, that's just the image of the small rectangles by the map phi, right? So all you have to do, guys, is just to add all these small areas here, right? So so what I'm saying, guys, is that so the area of the surface S can be approximated. So the area of the surface S. Okay, so it's approximately given by, so we're gonna have all these, you know, rectangles. For example, you know, you can call this rectangle here, this is the rectangle delta, you know, VI, for example, or delta UI and delta VJ, for example. Okay, so you have all these rectangles here, right? So there'll be the area of the surface S would be the sum. So it can be approximated with the sum of, again, the area of the images of these small rectangles by the map, by the function phi, which can be approximated with the magnitude of this, the cross product of TU with TV, right? So this is a sum, let's say ij going from 1, let's say, to n, you know, magnitude of cross product. This is, let's say, Vj here. Vj. And of course, there's this delta ui, delta Vj. And so, of course, the idea would be to take the limit when n goes to infinity. So then the area of the surface S is actually limit and going to infinity of this sum here. So this is cross product here again. J cross J, and so that will be, of course, this is a Riemann sum, right? It's a Riemann sum, so then the limit would be a double integral, okay? Because of course we have two indices here, I and J, so it will be a double integral over, of course, the region D of the cross product, the magnitude of the cross product of TU with TV, you know, DU, DV. Okay. Okay, so that's our formula. So what we are saying, guys, here is that so the formula is the following. So if you have so surface S parameterized, okay, by phi of uv. This is, of course, you know, x uv, uv, and z of uv. Okay, and we need this phi to be 1-to-1. One-to-one and smooth. Okay, except, as I said, possibly at the boundary of the region D. Okay, then the area of the surface S is just the double integral over D. Okay, remember the map phi here, phi, it goes from some region D in R2 to R3. So it's double integral over D of this magnitude of the cross product TU with TV, DU, DV. Okay, so that's the area of our surface S. And again, guys, that was, again, the idea is just, you know, take a small rectangle, so you divide your region. Let me come back to here. So you see what I did. This is you start with this region D, right? So the image of D by phi, that will be your surface S. So what you do is you divide D into small, very, very small rectangles with the sides equal to this delta U and delta V. Okay, so you divide this into very, very small rectangles. And then you take the image of these small rectangles. So there's gonna be some small small surfaces here. And all I am saying is that these small surfaces here, like this one here, can be approximated with this approximated with the magnitude of this cross product of this TU with the TV. Okay. Okay. So let's have an example. And well, we have 9 minutes. Probably we're gonna have just enough time to do one example. So probably next time I'm gonna do 1 or 2 more examples. Okay, so let me just do one example. Let me do the example of the sphere. So so we're going to compute the area of a sphere of radius A. Okay, so again, what I mean by a sphere, it's just a ball of radius A, right? This is here's A here somewhere here. This is A here and A here. All right. So the radius is A. We know the parameterization of a sphere. So we discussed this last week. So phi of UV would be, so this is of radius A. Okay, A is again, A is fixed number here. It's fixed. A is supposed to be fixed number. Okay, that's the radius, it's fixed. Could be radius 1, could be radius 2, right? So parameterization of a sphere of radius A would be actually A cosine U sine V, A sine U sine V, right? And A cosine V. U is between 0 and 2 pi, and V is between 0 and pi. Okay. As I said, we need this parameterization phi to be 1-to-1 and smooth. And as I discussed last week, there's a problem when V is 0 and V is pi. But I mean, 0 and pi, they are in the boundary of this, the interval here, right? So, so this phi here is, 1-to-1 and smooth, except at V equals to 0 and pi, and so this is 0 and pi. They are the boundary of my interval, right? This is 0 and pi. They are the endpoints of my interval. So that's okay here. Okay, so we want to compute the area. That's it's fine. So, but that's okay because 0 and pi are in the boundary of the interval 0 pi, because 0 and pi are in the endpoints of my interval, so they are in the boundary endpoints of my interval, so they are in the boundary of my region D, the boundary of D. Again, D is the region D here, so U is a 0 to pi, so 0 to pi cross, and V is a 0 pi, so cross 0 pi. Okay. Okay, so that's for, again, we need this hypothesis 1-to-1 and smooth, except at the boundary. Anyway, but again, in the homework, guys, or in the test, I'm gonna just make sure that it's their parameterization is 1-to-1 and smooth. If you have to compute the area or something, okay. Anyway, so all you have to do, guys, is to compute, T index U, and so step 1. Okay, so you have to find T index U and T index V. I mean, we did it last week, except, for example, just a difference here that we have this radius A. It's not A, it's not necessarily 1, but it's just a constant. So we did it last week, and then we computed. So step 2 would be to compute TU cross TV. So again, this was done last week, except that now the radius is a random number. A is not necessarily 1, but A is just a constant. So just I'm gonna just keep the constant here, and so the answer, I'm gonna just write down here the answer. I have the answer for this. So if you compute TU cross TV, then this should be equal to this vector minus a square sine square of V cosine of U, okay, minus a square sine square of V sine of U, and then minus a square sine of V cosine of U. Okay, so this is exactly, again, this is exactly what we got last week, except now there's this minus a square, and because my sphere is of radius a, not necessarily of radius 1. Anyway, so if you do now, so step 3, you have to compute the magnitude or the length of this vector. So that will be, so you have to compute the magnitude of this vector. So what do I mean by the magnitude? So that's the square root of, so the first term, the first first component, the square of the first component plus the square of the second component plus the square of the third component, and then we take square root. Okay, so it's the square of minus a square sine square of b cosine of u, so the square plus the square of the second component plus, and I don't have enough space, so no, I'm gonna just write it probably here, and square of minus a square sine v cosine u square. Now, if you compute this, guys, it's you're going to use the trig identity, cosine square plus sine square equals to 1. So after probably 1 or 2 steps, I think 2 steps. So here, use, of course, we're going to use, sine square plus cosine square equals to 1. So if you use that, then you end up with just a square sine of v. Okay, so then the area of a sphere, just the double integral of this, a square sine v du dv. So u is between 0 and 2 pi, and v is between 0 and pi. Okay, and so this is just a is again, a is a constant. So all you have to do is just integrate sine of v. It's not so it's not a big deal. And so this is going to be equal to 2 pi a square integral of sine of v. It's minus cosine of v between 0 and pi. And so the answer, cosine of pi is -1 minus -1 will be +1 minus minus there'll be plus 1, so that's 2, so that's 2 times 2, that's 4, so the answer is 4 pi a square. Okay, so this is the area of a sphere of radius a. It's 4 pi a square of radius a. Okay, so for example, if the sphere is radius 1, then the area of the sphere of radius 1 is just 4 pi. Anyway, guys, I guess I'm gonna stop here. We'll have more examples on Thursday, and then we're gonna start, of course, a new section, the scalar surface integrals and vector surface integrals. All right. Please don't forget your homework 5. It's due this Thursday. And again, still, if you have any question, just email me. All right. Thank you, guys. And guess I'm gonna stop recording here.